Good evening, everyone. I hope that you are well. My name is Mulebogal Kulwane, and I currently am based at the South African Astronomical Observatory in Cape Town. And welcome to the second session of time series analysis. Right, in the morning we dealt with time series analysis, and today we have the privilege of being hosted by Professor Reinaldo Rosa from Brazil, who he's based at INPE, which is the national facility that deals with space science in Brazil, and he will be giving us a short lecture on time series analysis. Right. So please, guys, remember that we are live streaming our sessions as well as recording. Should you miss anything or wanna go back to our sessions, we are live streaming them to YouTube. And to Professor Reynaldo, over to you. Thank you so much.
Hi, Moleboge. Thank you very much for this kind introduction. Hi, everyone. It's a pleasure to be here. Before we started, I just want to show you my portfolio. Okay, in my portfolio, you can find out all the informations on my work, and I can send you the link at the final of the lecture. So there are many areas that we are working on, and we have also in Brazil, in our institute, the Applied Computing Graduate Program. Okay, it's open every year for around 50 new positions. Everybody is allowed to apply, even from other countries than Brazil. And please let me know if you are interested on that uh, just after the lecture. I will be here for a couple of minutes so we can talk about that. Okay, so I will be here trying to bring to you some basics, very basics subjects on time series analysis for astronomical data. This is what I call module one. So next week we go to the module two, where you see resources from artificial intelligence, mainly bringing in the pipeline the layer for explainable artificial intelligence, which is the most important issue in AI applications, at least from my point of view. And then the module two next week, I will explain why I I think like that concerning the XAI, even for astronomical data. For this class today, I would like to stress that what we call astronomical data here maybe can see in two ways. One way is of course, data from astronomical observatories, right? We have also data, and if we call, uh, if we go to the mainframe of astronomical observatories, we will find out many different, of course, windows from optical and from optical to high energy physics. But you can also see this name astronomical data as a big data. We okay, a lots of data. In this class today, we are not facing this problem. Okay, in the class today, I go to the basics, very basics concepts on time series analysis, out a little bit outside from the classical average moving approaches. Okay, I want to bring it to you what's in practice is very important to know on time series analysis. I mean the basics on that. And we are going to to pave the way to do to move forward to XAI, to the next module. Okay, so that's the idea for today. Our focus in this lecture will be in two efforts. The first one is conceptual. Okay, let's try to bring to you some very fundamental concepts on time series, not only for astronomy, but in a general vision. Actually, this course was prepared not only for astronomy, but also for physics. But of course, the concepts here will be very general, so we can bring them to time series applications, okay? Even in economy, even in social sciences, and so on. So concepts, pay attention on concepts. And also, we will try to bring to you operations. So it should be focus on operational stuff. What means that? It means that we have input of a time series. It goes for a kind of operational algorithm on that data, and then we have an output. And we should be able to understand what this kind of output is going to improve our knowledge about the underlying process that was responsible to the fluctuation patterns that we see in a such time series. Okay, so important here, understanding the concepts plus knowing how to implement them. That's our goal here. So how will you learn? As I told you, let's introduce the main ideas, intuition and theory based on concepts. Very, very basics ones. Then we go to operations. We translate concepts into computational operations. Of course, we need some practice. So I will start with a concept, explain some tools, not going in very deep in mathematics here. We don't have time for that. But we need the minimum basis to go to hands-on in Python. As I understood, all of you already have some experience in Python programming. So we go to practice that. I'm going to show you a hands-on. Then after that, you can practice that by yourself. So we can implement together in the Google Colab with real astronomical data. Of course, we are not going to do this implementation here, but we can do after the lecture. But I'm going to try to explain you the algorithm as much as I can. And then we go to interpretation. That's a very important part. We should be able to interpret results and connect it to the physics behind it. It means to understand the underlying process that was responsible to a time series at the input. And then, of course, we discuss real applications. We apply the methods to solve a real astronomical problem or physical problems in a general way. For each set of concepts, we go to operation, hands-on Python, interpretation, application. Let's see if we can do that in a proper way in this class. I hope so. Let's try. So let's build a conceptual understanding, practical skills, and scientific insight. And I think that's the teaching pattern in the nowadays. We cannot avoid this kind of approach because I think we need to be agile. We need to use the agents as much as we can in a very responsible way. So let's see how it happens. What we will not cover in this course, that's very important. okay, will not focus on the classical time series modeling, okay? That are kind of approaches that is very easy to find out in the internet. There are thousands of material, books, booklets, and also algorithms, okay? And why not? Because we don't have time for that. Our time is limited in this course. Those methods require strong assumptions, linearity, stationarity, and many others that we are not facing here, and that are often unrealistic for astronomical data. Actually, those models, they are not the best for data that are often complex, bringing a very high level of non-stationarity, noisy, irregularly sampled, and Rayleigh dimension. Of course, there are approaches nowadays for those moving average tools using AI. So in the next class for the module 2, next we'll see something about that. But in the hands-on, I will show you only one application, very sharp application about this, just to allow you to understand what's the whole of such approach. The current emphasis in astronomy is shifting toward data-driven and machine-learned approaches with interpretability. So this is, we can say, a very difficult to bring this kind of improvements due to many technical concerns. So our focus instead will be try to emphasize in statistical and spectral analysis, feature extraction and representation in the module 2 machine learning approaches, and mainly in explainable and physical interpretation. So the ones that can, need to go further and they want to understand those classical approaches, there are many books. I can recommend that, and okay, for you. So it's in the material. It will be also in the booklet. And actually, I will provide a course booklet for review and hands-on practice, extra hands-on practice from today to tomorrow. So don't worry about that right now. Here, that is also for the classical approach and also the modern one. I recommended this book, Apply Time Series Analysis and Forecasting with Python, from Huang and Petukina. And this is for free in the GitHub. Okay, you can go there, and there are many books also, not only this one. Okay, so we can get the PDF there. Our reference tools for practice will be Python and traditional libraries. In this class today, we are not going to use AstroPy, only for machine learning approach in the next class. And but there are many reasons why to do that in a Python framework. And there are many libraries for scientific computing. I know that all of you have some experience with Pandas, SciPy, NumPy, maybe not yet with AstroPy, but you do that in the next class. And there are many others tools that libraries that we can work based on our requirements for visualization, time series analysis, machine learning, explainability. There are many things here. Okay, So this material is available for all of you. So I sent that for, so I'm not going reading everything is here. And let's start in the basics. And please write down your question and ask them when I open the floor for questions during the class, okay? Okay, so let's take a look here on the fundamental pipeline here. As I said, we have as input a time series, okay? Time series here is a signal or flux or a general amplitude that has been measured by a astronomical instrument or physical one, or even from some kind of simulations, computational simulations, why not? And then here we have time. In astronomy, you have light curves, spectroscopic signals with the light curve counterpart, flux measurements, event rates, gravitational wave strain, and much more. So this input data goes to the time series analysis pipeline. And in this basic course, we will see only this part that's above of that. It means statistical and spectral ordinary analysis. Okay, we are based to find out metrics from histograms, probability distribution function, trying to understand mainly when we have a non-Gaussian signature from this kind of input data. And this, for do that, we work on ensembles. Doesn't matter the autocorrelation function in this type of data. And we will see also the power spectrum density, from where we can understand better the underlying process. For example, if you have a turbulence here, some weak turbulence or fully developed turbulence involving this fluctuation pattern, using only one metric here, that's the power spectrum index, we can infer some knowledge about the underlying process. Okay, so there is no AI here. There is no, of course, there is no AI, there is no XAI, but there is, that is fully interpretable. Okay, and this is the basics that everyone should know before go to very other complex approaches using much more complex tools. And this we will see in the second class, where we go to machine learning analysis. There are at least 5 important approaches. The first one is clustering, classification, regression, association, that it's not so common in astronomy, but you can use association, and of course prediction or regime characterization. Prediction is very difficult, everybody knows, but we can say we can predict regimes, transition from laminar regimes to turbulent regimes, and so on. Okay. If you have some questions, you can ask now. If not, I will change. Let's move it forward. Okay. So, first of all, let's take a look on the main types of time series in astronomy. Okay. I'm addressing here from solar activity to cosmic transients. So it means we are talking about a wide range of time scales and physical process. Usually nonlinear process involving many variables. So we are talking about complex process, right? The most simple ones are here. Examples are sunspot number, that will be, this is a classic indicator of solar activity, and the 11-year solar cycle, magnetic cycle, which should explain any analysis here, must explain the very well-established theory that we call solar dynamo theory. And this will be our data for our hands-on of the day. We have also stellar light curves, usually, especially the almost periodic ones for periodic variables. So there are many different objects that are in this kind of generating this kind of fluctuation pattern, pulsating stars, eclipsing binaries, rotating stars, and so on. We have also exoplanet transits, also very important, and active AGNs that everybody here, I'm pretty sure, hear about that at least once in his life. So it comes from irregular variability across multiple wavelengths, and this is a very important in multi-messenger astronomy. Also, it is a little bit more irregular than that one, for example, and that one. We have also supernova light curves, luminosity evolution, okay, and facet transients. Supernova could be one of that also, one class of that. And we have a facet transients, gamma ray bursts, kilonova, fast ray bursts, and many others explosive events. Okay, so there are many sources on this kind of data here. So it means that astronomical time series span an enormous range of time scales, from milliseconds to centuries, and reflect diverse physical processes. Periodic process, pure stochastic process, nonlinear process, chaotic process, and multiplicative cascade, multifractal process, from where we can have extremes that sometimes are endogenous, sometimes exogenous. Okay. In the second module, we will see in detail those kind of concepts. So our course structure here goes from basics to explainable AI, as I told you. So the module today, we use, as I said, sunspot number series for the hands-on. And for the second one, we use many different data, okay, based on AstroPy scripts, Python scripts application. Okay, so our attention here for this class right now, from the beginning to the end of this class today, we'll focus on the statistical and the spectral standard analysis for a given input that should be a time series, okay? And but of course, at the final, you see that that's a bridge to more sophisticated approaches based on artificial intelligence. So time series means we are trying to understand, to extract as much as we can information, okay? This kind of information, usually metrics, one or few metrics that we can extract from the time series, we go to understanding. This understanding sometimes brings something new and that we call discovery. So even we are not using machine learning, AI, and even it's not big data, we have the same pipeline that is very famous now with this fashion approach that we call machine learning. Okay, so it's not a novelty in this kind of approach. That's I want to stress here. First question, first concept. In very basic understanding, what is a time series? Time series is a sequence of measurements of a quantity ordered in time. Sequence, that's important. So there is a kind of time resolution involved here. And it describes how a system's evolved over time for what we call a sample window. Okay, of course, we cannot be sure that the whole evolution of the process has been observed with just a time series. Okay, and also with the time resolution we are taking the data is the proper one to understand fine structures or some kind of hidden fluctuation pattern. So we need, in that case, we need to improve, for example, the instruments, okay? Sensitivity, time resolution, sometimes spatial resolution, and sometimes the frequency band, okay? And we know that in astronomy, astronomical light curve alone, okay, doesn't mean too much on the physical process. We need to bring together the spectra. Please don't be confused about the spectra concept here. We are going to take spectral information from time series, but it's different than the spectral data that can get from spectroscopy, okay, from the telescopes, let's say like that. But what's important here from the concept for time series? We have this time resolution, okay, we call delta t. So delta t is constant along the time series for each difference in time from t I plus 1 minus ti, we get the same interval in time. Okay, so in a very simple way, we call that time resolution. And so this is a regular time series. Okay, so we have, if we have a missing information here, some kind of sparse data, we can infer how many points we are missing. So that's also important. And we have also the mean of the average of those amplitudes fluctuation, and we have the variance or the standard deviation, okay, that defines the concept of dynamic range. If you have a max amplitude minus a minimum amplitude, we define that a dynamic range. That's a very important concept concerning the 3 sigma approach. When we have like extreme fluctuations, doesn't matter if it's positive or negative, it can go beyond the dynamic range based on the 3 sigma. Okay, so so we have any measurements defining the time series, okay, and what is important here is to realize that we have 2 statistical metrics here. The first one is the mean that everybody knows since the undergraduate course, and we have the standard deviation. The standard deviation to be calculated depends on the mean. The means here, okay? So in the proper language, we call that the first statistical moment, and then we have a second statistical moment. We are going to talk about that in a minute. But what are the mean and standard deviation from a statistical point of view? What do they really represent? How are they related to the shape and properties of the distribution of the data? The statistical one, the statistical model, let's say like that, the histogram, and then the PDF, the probability distribution function. Okay, that's a very important to infer if you have a Gaussian, non-Gaussian fluctuation pattern from the time series measurements. Here, it's very important to address why we are using A here, not X. In some books, you see for time series, you use X, I, and TI for time. Sometimes they use Y and X here. It's a very confusing stuff. But here, I prefer to use the letter A for amplitude. Doesn't matter which kind of amplitude, okay? Because there is the amplitude equation theory from where we have many models for turbulence, for weak turbulence, for many kind of very complex systems. But of course, it's a very realistic one because it's related not only with one space dimension, but you can have limpedness of X, Y, and Z in a Euclidean framework. We can also use a spherical and other coordinate systems. And we have a time here. Okay. In our approach here, we are not assuming we have any information concerning space. We are just having information concerning time. So that's a time series. So here, AI is used to denote amplitude along time. Spatial coordinates will be used when we extend it to spatial temporal approach, or space-time is not a good spatial temporal series, okay? And then we start to talk about pixels changing along the time, and also voxels changing along time. So just to be sure and make it clear, okay? So what are statistical moments of a time series? Are quantitative measures that describe the shape of the probability distribution of a given variable. They summarize the different aspects of a time series beyond the mean and standard deviation, capturing its structure, asymmetry, and tail behavior. That's very important to understand what a kind of extreme fluctuation brings to the statistical model. And definition of any other moment about the mean is given by this formula. I'm pretty sure everybody here saw this kind of description in statistics courses, right? And the most common moments are the variance, skewness, and kurtosis. Okay, this is we call Pearson kurtosis. Okay, when you do this difference over 3, so it means for the Gaussian, the kurtosis will be equals to 3. So we'll be able to building a parametric space where we can classify Gaussian and non-Gaussian process only based only on the kurtosis a square of skewness that we call Cullen-Frey parametric space. You'll see that in a minute. Okay, why are moments important? Reduce complex data to informative numbers, quantify the level of fluctuations, identify systematic increases and decreases or skewed behavior, assess tail behavior, determining the probability of extreme events, and also behaves as a support modeling, a guide to choice of statistical models and noise assumptions. As I told you, as I didn't told you actually, we are not dealing with noise right now. We are not taking care about pre-processing in this course. But of course, we will be talking about noise at the end of this course today. Then that's, as I told you, that's very important for extremes and departures from Gaussianity. We have the concept of quantiles, also very important. Okay, I recommend you for everyone do a kind of review, okay, on those concepts, the quantiles. And we have the 3 sigma rule Gaussian case, okay, when you have almost 100% of the data lying within this interval, okay. So we call that interval for information and interval for noise sometimes. So extreme fluctuations are points that are beyond the 3 sigma, and it means very seldom we found that in the measurements. But in astronomy, that's a very common one for solar flares or stellar flares, bursts, transients, outbursts, measurements from shock waves in plasmas, and so on. And when the distribution is not Gaussian, when you have what we call leptokurtic pattern, have tails, okay, more extremes than Gaussian. And also we have the Plackti-Kurtic concept for light tails, fewer extremes than Gaussian. Okay, so there is this kind of behavior when the non-Gaussian signature comes in the data. This affects risk estimation, detection, thresholds, and model selection. Okay, and there are many examples in astronomy. Okay, so it's important that we will be able to compute, interpret, and use the moments in practical analysis and machine learning models in the next class. Okay, from time series to the histograms, why extreme matter. Of course, histograms reveal the empirical distribution of amplitudes. When extremes occur, Gaussian models may fail, and we need another kind of PDF models from outside of the central limit theorem. So we go to the generalized extreme value distributions that sometimes become necessary. So a histogram is an empirical estimate of the probability density function of a variable. We divide the range of amplitudes into bins. Okay, we choose those bins. The amplitudes into bins is a kind of setup of the algorithm to get the histogram. And the weight of each bar is proportional to the relative frequency of values in that bin. It's a counting algorithm, right? For each amplitude scale that's in the signal. As the number of samples increases, a bin size decreases. The histogram approaches the true PDF. Okay? When there is this kind of extreme, okay, we have changes in the model that sometimes is not, we cannot find the best fitting model just change the values of mean and sigma. So based on the statistical moments, we interpret the distribution as the center where most values lie. Of course, you have another concepts based on other metrics beyond the mean, but we are not going to talk about that here. We have also a spread that is related to the variability, how dispersed values are, the shape that bring information on the asymmetry, left or right tail dominance, and the tails for how often extreme events occur. So as an example, we have here a white noise, okay? This is a white noise. So if we count all we do the bins here. So the bins that are, this region of the time series is much more dense than the other regions. So that's why the histogram has this behavior going to this maximum at the center of the time series. Of course, we go to the Gaussian, the normal one, and we play with two gradient moments here and we get the best fitting we can using that. This is a very good fitting because, of course, this is a white noise, and white noise is a kind of a fluctuation pattern described by a Gaussian process. Okay, so, but sometimes you have this kind of extremes, okay, occurring along the evolution of the data. So what you find here is what we call Pareto-like distributions, okay? That is not Gaussian, it's a non-Gaussian one. There are a family of different shapes, and sometimes those shapes are the real underlying, reflects the real underlying process on the system, okay? The Gaussian is not an attractor anymore, like playing with the dices, okay? If you have one dice and you have many dices, the more dices you have, the Gaussian is an attractor for playing with dices. But Gaussian is not attractor for many systems, okay? For example, we have published this analysis for extreme event dynamics in the formation of galaxy-sized dark matter structures. Okay, we applied the generalized extreme value along the redshift variation for simulations from Virgo consortium. This is N-body simulations where any single particle is a galaxy. In a box, in average, if it's 100 megaparsec, here it's in the cosmological limit here, so it's a cosmological evolution simulation based on the lambda CDM cosmological model. And what we get here, varying the redshift, is a very non-Gaussian model. But it's also very common, and it reflects what we see here, okay? Clumps of galaxies connected by filaments. And then we have some... Yes, please? Any question? Hello? Okay, may I go forward? Hello?
Yes, please do go forward.
Okay. So So for the internet hubby, we have also the same kind of non-Gaussian fitting. We have the hubs and the number of connection for any hub. So you can increase it as much as you can the number of hubs. This pattern will be not changed. Okay, never that will be changed. So it's a kind of a fractal structure or something like that. Also, we find that for cosmological data. So take a look on this paper, and if you want to go deep in the statistics of extremes, I recommend this book from Gumbel. Actually, Gumbel is also the name of one of the non-Gaussian distributions. So we will see when you have extremes breaking Gaussian assumptions. Okay, you see very small changes in the Gaussian fit comparing to the generalized extreme value fitting. Sometimes Gaussian works well, sometimes not, and Gaussian underestimates the habits that are here in the tail. Okay. So why Gaussian fails in the tails? Gaussian distribution have exponentially decaying tails. Extreme events occur more or less frequently than Gaussian predicts. This leads to poor estimation of extremes, return levels, and higher event probabilities. So we can also use it instead of the Gaussian formula for the normal model, we can use the generalized extreme value distribution. It's a kind of, it's not based on the same statistical moments. It has its own parametric set of values like location, scale, and shape that goes to this formula. So we can play with those three metrics to get the best fitting result from your real histogram. Okay, so there are some very special kind of PDFs. When you have heavy tail, we call Frechet type, exponential tail Gumbel type, and bounded tail Weibull type. Okay, and this is a very tough application. We sometimes you don't need to go to this fitting. We can, in our hands-on, we will try separate non-Gaussian PDFs like gamma, log normal, and log normal is a very common one in nature. Okay, when normal Gaussian is not the best, the first step is trying fitting the data using based on log normal. Okay, and we can also do that with the cumulative distribution. Okay, and there are many examples for applications since solar physics to gravitational wave bursts. Why are we going with GAV? With GAV, we have a realistic estimation of extreme event probabilities, better risk and return level evaluation, more reliable thresholds for event detection, and improved input for physical and machine learning models. Okay. So from time series to histogram, we need to take care also about bimodal histograms. So what means when you have a bimodal, and what kind of approach we can use to try to model this kind of histogram based on a given PDF. Okay, this is a very important question. You see that when it happens, it's better to go to the first machine learning application that we call KDE, kernel density estimation. This will be the first hands-on in our next class next week, okay? So how histogram is built? We have, of course, the counting of amplitudes here, NEI. So the probability I is NEI by N times delta A. N is the total number of samples. So that's a very common algorithm. So Gaussian comes from this kind of model related to two statistical moments. And we use fitting models to the histogram to trying to find out the best PDF. Then it's a very, very empirical experiment. Okay. Of course, the expertise of the analyzer is very important when we are trying to find out the best PDF model for a given time series. Or any data, not only time series, okay? Any ensemble. Alternative estimation, we can use the KDE, kernel density estimation. This is a kind of a machine learning. It's a statistical concept, but it's the best adapted for machine learning applications, trying to optimize a kind of searching function. Okay, so in the next class, we will start using this kind of approach for bimodal distributions. And there is also some kind of family of testing for Gaussian. There is the Agostino-Pearson test, where we call we just bring it to a kind of partition a moment based on the kurtosis. Okay, so it's based on the chi-square concept. I also recommend you take a look on the concept again, on this concept again, and we can define a kind of a workflow here. We have the time series, the ensemble. I mean, for the ensemble, it doesn't matter the timing sequence here. Then we get the histogram. Then we fit a candidate PDF, Gaussian, or even a KDN, if there is a bimodal behavior. Test the normality with this kind of Pearson test, the Agostino-Pearson test. Go to select the best model and interpret the distribution that can help us to infer properties of the underlying process. So the key takeaway here, histogram show that the data do. PDFs tells us may mean. In practice, we compute a histogram, fit models, use different PDF approaches, perform normality tests, and evaluate the fits using many Python libraries, scripts. Okay, the goodness of fit tests for a time series can also use two complementary approaches that we call Kolmogorov-Smirnov test and the quantiles plot. Okay, so we have the time series input. We have this fitted PDF on the histogram, and we have the Kolmogorov-Smirnov test. It's based on the difference of empirical CDF and the theoretical one. And here we have also the QQ plot. You see that's in the hands-on. The points close to the red line it's a good agreement with the Gaussian. Okay, points above the line shows that we have a heavier upper tail than the model. Points below the line, a lighter upper tail than the model, if it happened like here instead of here. Systematic curvature is a mismatch in the distribution shape, and is a very good test of non-Gaussianity at the end of our pipeline. Okay, so summary of the workflow: input time series, fit candidate distribution, histogram plus PDF. Okay, we do the two tests here, the Kolmogorov-Smirnov and the QQ plot. This means only deviations of the shuffling data from the Gaussian one. Okay, so here we have our pipeline to show application in the sunspots based on pure statistical ordinary analysis, but we can also do the time series analysis in a spectral domain. We can bring more information on the underlying process if you compute the power spectrum density using Helsch's method and the analyzing frequency period space. You can also use the fast Fourier transform. I'm not going to this kind of detail. And the outputs here are 4 complementary views of the spectrum that can reveal periodicities, scaling behavior, and dominant physical process. Okay, and we can also try to find out some very, very common strong periods present in the data, doing the power spectrum density versus periods that you can find, especially in time series like this one that comes from the sunspot number. Okay, and so that's what I recommend, that you training the algorithms. Okay, you can also change the input for another kind of time series from astronomy or other kind of data, like in physics or even in economy, stock market time series, and so on. So the power spectral density, it's very easy to get. Actually, we put this is what we call, based on the Wernicke-Sheen theorem. You can get the power spectrum density against the frequency of each set of amplitude values here. And we use a minimum square approach here to get the best linear fitting, where we call inertial regime, and then we get the value of a spectral index beta. For example, if you have a time series from colored noise, for white noise beta equals to 0, for pink noise beta equals to 1, and for brown noise or red noise, that's very common in physics, especially for diffusion, we have a beta equals to 2. Okay, we can also identify characteristic periodicities, maximizing the dominant peaks in the PSD. Okay, like we see if you apply PSD versus period, we get 11-year cycle, and maybe other sub periods in the sunspot fluctuation pattern. And we can also we have a kind of problem here. I just mentioned here that sometimes we are dealing with short time series. There is no statistical meaning for such sample. So we need more data. Why? Take a look on the power spectrum. In the power spectrum, we have a number, minimum number of decades, because it's a log-log a plot. Okay. When you have only 1 or 2 decades, it's very difficult to find out a good fitting in order to get a good value for beta. Okay. So, as I say, it will be very important to get a robust data when you have a PSD based on at least 3 or more decades in this power spectrum. Okay, so then we can get a very robust beta. If you are looking for characterize, for example, turbulence from a data, we are trying to find out here the minus 530 from the Kolmogorov empirical turbulence model. And physics, for example, we will find out many deviations of the minus 530. It means that the magnetic field plays a very important role on the underlying physical process, generating, for example, MHD turbulence. When you have a straightforward analysis on the plasma process. So when we have a short time series, in order that it will be very difficult to get uh, a robust beta from, let's say, playing with 2 or 3 or maybe 4 decades. Let's say we have only 100 measurements or maybe 200 measures. This is a very common amount of measurements from a transient light curve, for example, for a supernova. When you have things like that, and also for some kind of radio bursts that happens in the sun from the solar corona, this is an example in this paper. So when it happens, we can use another kind of spectra based on the trended fluctuation analysis that we call DFA. Okay, and DFA gives some spectra like that. We don't have a problem of decades here, so this value of alpha also gives us information on non-Gaussianity, and also from the underlying processes, if it's weak turbulence or pure diffusion or something like that. And there is a relationship between alpha and beta also by the Vinoy-Clichy theorem. I'm not going in, this is a very technical, deep detail, but I'm not going here. I think we don't have time for that. We already spent 1 hour, so that's one paper that I recommend reading to understand also how we treat short time series instead to use for the spectral ordinary analysis, instead to use power spectrum density, we use the trended fluctuation analysis. The trended fluctuation gives us this kind of spectra, and they can also use DFA as it's very robust for short time series, because it's not based on Fourier transform, fast Fourier transform, but it's based on the Holder exponent for fractals. I can use small windows to track, okay, to trying to make a prediction, a regime prediction from a very ordinary fluctuation to a more complex one, calculating alpha from different windows. That's what happens here, okay, for each burst. So the more complex, we get different values before extreme like that, that's in the solar flux unit, vary in time for solar radio bursts. The symmetrical ones here. 3.0 gigahertz is the the spectra, the radio astronomy that we needed to observe this kind of radio bursts from the sun, active sun. So the data that we are going to the hands-on is based on the sunspot numbers that has been counted since the 17th century, 1700 in the Gobi Desert in China. There were many registering sunspot numbers at that time using the very low seeing and very good atmospheric properties in the Gobi Desert, so they could observe and counting the sunspot numbers without any optical artificial device. Okay, just by eye. But more recently, we have a very robust counting for sunspot numbers. Okay, since the minimum Maunder, I'm not going to detail here, but we have this number of cycles where we see there are the 11-year magnetic cycle, but also each one is different than others. It has each its own a fluctuation pattern. Okay, the people have shown that if you take only the high frequency from this kind of data, you see there is a kind of chaotic behavior, noise behavior here, but not a white noise, of course. It's a non-Gaussian, very non-Gaussian noise, and also some chaotic behavior from the variation of the maximum along the time. Okay, so there are many particularities on this kind of data. Okay, so this is the dashboard for the hands-on, and I recommended that we now go for a break. Let's say 5 minutes or 10 minutes. What do you recommend, Lebo?
Prof, we can do a 5 or 10. Whichever one you choose. We're open
Okay,
to.
let's break for 10 minutes. Could be a small coffee, and so we'll be back for the hands-on. So
Perfect.
we will move to the Colab uh, uh, laboratory to run these applications together and try to explain in practice how to perform this kind of very ordinary statistical analysis on typical astronomical data, that is the sunspot measurements, daily measurements. Okay.
Perfect.
Before I leave, if you have any questions, please let me know. Just okay. I'll be back at 15 past 6 for you guys and 15 past 2 for me. Okay, okay, guys, let's start again. So, so what what's going to be now? We are going to this pipeline in the Google Colab. We start with the data acquisition, data preparation. Actually, we don't need too much preparation here. Just bring some concepts here. In the machine learning concepts for the next class, we used to say we have attributes here and instances. Okay, here. Instance sometimes is not time. We don't need to work here with time. You know that. But when you are talking about time series, we have the attributes, and the first one is always time. Okay, that's a very important detail that we need to stress here. Then we go to the descriptive basic statistics, mean, median, standard, variance, skewness, kurtosis, minimum massman, and percentiles if we need. We need that for the QQ test. Then we go to distribution analysis. We go to the histogram, the Agostino Person normality test. Okay, so when P is less than 0.05 is not a Gaussian, and when it is more than 0.05, it's a Gaussian one. The Coulomb-Frey plot, we have the square of skewness here, okay, and kurtosis in the axis is the square of skewness. So it's 0 when they have the Gaussian one, and we have a 3 when this kurtosis is the Gaussian. So you see this in detail. Okay, once we find out the best PDF in the Coulomb-Frey graph, we use this to play the fitting on our data, our ensemble. And we can also do the tests that I already showed you. We go to the units of fit tests, and we finish with the spectral analysis. And then our interpretation about this. This is a typical pipeline flow for a basics course. Of course, most of you maybe has applying this kind of analysis since it's a very basic one, but as I don't know exactly the expertise of each one of you, I'm doing the basics here. Okay, so I'm not sure if Molebo already sent this scripts for you, this notebook. Okay, but of course it's available for everyone. It's part of our course. So the first part, some parts of here are in Portuguese. I apologize for that. Okay, but the first we are using in this data acquisition script pandas, NumPy, and matplot, pyplot from from the Plotly library, and we can get the data straightforward from the GitHub repository. Okay, this is in the CSV format, and it do just the verification of attributes and instances, and then it plot from a pandas table the time series here. Okay, so if you run, and also here what I'm applying in just a glimpse for you on the moving average approach, we can apply ARIMA method just to get, the moving average for the whole time series. That's a very important approach because sometimes we need this average to understand, to find out some other frequencies on the data. You see there is a low frequency here that only the moving average approach can show us. So that's one kind of a very important application coming from the very classical approach that we call Jenkins box time series analysis. You can also building models from this classical approach. A model, for example, only for low frequencies is possible to do from the average moving techniques. We can also get the spectra from the Fourier fast transform. Okay, But for this kind of data, as I told you, there is not too much points. So instead to use the fast Fourier transform, we will use the Helsch window. That will be much better to get the beta value, trying to say something about the underlying process in terms of fluctuation pattern, especially from the very high frequency to the lowest ones. So the second one, we are loading data in, let's start here, do that again. So here I'm just plotting the sunspot time series plus the average, and also the sigma and 3 sigma thresholds here. So we see there are many extremes beyond the 3 sigma threshold. Of course, you can also normalize this time series between -1 and 1 with zero average. But for this kind of analysis, it doesn't take any advantage comparing to this one, because you're not applying, let's say, any tool that depends on the normalization here. And then the second one, what it does, just calculate the moments, the statistical moments, okay? Do the basic statistics. We are using here the SciPy stats. From this library, we imported skew and kurtosis, okay? And then we can get the values for mean, variance, standard deviation, central moments, skewness, and excess kurtosis. Excess kurtosis here means we are using the Pearson approach for k equals to 3 if it's a Gaussian one. And then we see the histogram. Of course, you can change the number of beans. Let's put it here like 80 beans, for example. So it looks like this one to 15. Okay, so it's one input that you can change in order to get more fine information on the histogram. So then we can try to see how is the value for P. Okay, P value is comparing the deviation of a Gaussianity based on the intrinsic distribution for each group of beans. So if you do that here, we see that the p-value is rejects the null hypothesis of normality, of course. Okay, it is much less than 0.05, and we can see visually that's non-Gaussian one. So then we go to the Coulomb-Frey. What means that we are going to calculate it. We are going to take the values of square of skewness and kurtosis and see where and I'm comparing with some non-Gaussian distributions. So what happens here? This is the Pearson kurtosis, which means Q equals 3 is the normal and 0 for square of skewness. So the Gaussian is here, the orange dot on the graph. And we have also values for the uniform distribution, exponential distribution, gamma distribution. And our data is around here in the Cooling-Free graph. So if you do that, you say, okay, let's use a generalized extreme value and play with the three input parameters. Okay, and but instead to do that, let's do something more logical in terms of very from the simplest analysis to the more complex analysis for PDFs. So as it's a very close to normal and is a physical interpretation, I would like to apply to test the log normal. Okay, log normal will be like a line here, like this. Okay, it can get also some very high level for squared schemes, but it comes very near to the normal one. So if we do that for a log normal distribution fit, okay, we will get a very interesting fitting. We can maybe improve that, change the parameters, okay, but it's a very satisfactory fitting, not a non-Gaussian one. And then we can apply the Kolmogorov-Smirnov test here. Again. So at this time you have a better value for D and P. And let's improve that applying a Weibull distribution. That's from generalized extreme value. So Weibull here. So I think Weibull was much better. And we can see that they use shape Q. We can change that. You can play with this. Location 0, because it's a asymmetric 1. Scale this value. We can change that. For example, we can put shape. We can increase the shape by 2. But we can come back after. Actually, that's the property of the Gaussian. And we can apply the KS test for Weibull. So we see that's much better than log normal. And we apply also the quantile plot. That's the ordered values and theoretical quantiles. So the red one is the Gaussian, the blue one non-Gaussian. Okay. So the non-Gaussianity here is very well characterized from this kind of analysis. Let's move to the spectral analysis of this Sunspot time series. What we are going here, we have outputs for time series, power spectrum dense plus power law fit, power spectrum dense with dominant peaks, and power spectrum dense versus period. Okay. When you get the PSD plus power law fit, to get the best power law fit, you just filter the peaks. That's why you don't see the peaks in this plot. And this one will keep the dominant peaks to have an idea about the main period and maybe some sub-periods that is in the underlying process. So this figure you plot the time series again. The second output will be the power spectrum density, and the beta is 0.88. Okay. The criteria to do that, I'm just taking a special window here to fit the best, but it can change, of course. the more data I have. You see, I don't have too much decades, as I told you before, only 2. So the trend fluctuation analysis will be very interesting to apply here. We are not going to do that here, but we can implement the trend fluctuation analysis and compare with the power spectrum density. And you can also have the expected theoretical value for alpha from the Wernicke-Sheen theorem. So we'll see also the dominant spectral peaks, 10.7 years. That's the very famous 11 magnetic periodic variation of the Sunspot's number from the dynamo solar dynamo theory. And here we have the characterization very well sharp for 11-year cycle when you plot PSD versus periods. Okay, there is another one here, a small one here. Okay, actually the theory says that there are some actually almost quasi-periodic behavior in other in low frequencies, and the final interpretation. So this is from here. Sorry, let me just correct. So the statistical fluctuations of the sunspot number are markedly non-Gaussian, exhibiting positive skewness and heavy tails. Spectral analysis reveals a power law background with spectral index beta 0.8, indicating long-range temporal correlation memory effects. Together, these results suggest that sunspot prediction is governed by a nonlinear multi-scale dynamical process rather than by a purely stochastic Gaussian mechanism. The observed behavior is consistent with intermittent magnetic activity generated by the solar dynamo operating far from equilibrium. Okay. So I will provide a course booklet for review and hands-on practicing from today for tomorrow. I will send that to Mole Borges. Mole Borges will send to you. Okay. And if you have any question, please tell me. I'll be back to the slides.
Hello.
Are there any questions in the chat?
Hello. Can you hear me?
Yeah, I can hear someone.
Yeah. Thank you for your wonderful presentation. I want to ask, in the first session today, we had the presentation about time series analysis, and the presenter highlighted some key parts I was fully interested in, the part of hot plasma. So I want to ask again the second time. I don't know if you could ponder on the hot plasma. Is it possible to use time series analysis to make analysis on astronomical plasmas?
Yeah, of course you can. You can. Astronomical plasma, mainly of the fine structures that we know comes from simulations, right? It's very hard to compare fine structure formation from the real solar plasma. We know much more about what we are trying to looking for from the very high performance simulation from MHD model. And there are many simulations, not too much time series, but few time series, showing that we have many fine structures forming in time. For example, when you have the interaction of multiple flare, multiple magnetic loops in the sun, and this analysis, all those analyses, is showing that the process is a very high complex one, and all of them are non-Gaussian. Okay, but so the big challenge is trying to find out which kind of frequency from the spectra analysis corresponds to a given particular process in the plasma. But this basics analysis, from my point of view, is the first one that we need to apply. And also, concerning your question, we can use that as the first step to do modeling validation. I mean, real physical modeling validation. Let's say I have some MHD process that has been simulated. I have some new data that comes from a very high sensible measurement. Then we can apply these basics to validate a given a new simulator for MHD for a specific plasma process. Not, of course, only in the sun, but any plasma behavior in astrophysical, from astrophysical sources, different astrophysical sources.
Okay. So if I get you, what you're trying to explain, sir, you mean there are other analyses that can be applicable to make analysis on hot plasmas or astronomical plasmas, not just only time series analysis.
Oh yeah, sure. Next week we will see machine learning analysis. Okay, machine learning analysis. We have that 5 that I show you. We can do clustering for different classes of patterns. We can do regression analysis to find out values that we still don't know relating to variables, different variables. We can also do association. For example, if it starts one small flare, solar flare in a given region with where the value of the magnetic field is well known, what kind of association is in between or among different reconnecting loops of the sun. So there are machine learning tools that you can apply to find out rules of association among different time variability among sources. Even for multi-messenger astronomy, you can also apply association techniques. And then we see all those techniques, how we discuss how it begins to be very important in the big data contest when you have, we need to be agile in the analysis because you have lots of data coming from, for example, transients. We have the problem of to construct very good brokers in order to make a very high level multi-messenger astronomy based on transients that comes from LSST observations. And of course, you know that we are facing on thousands of events in an hour. So it will be very important to apply more sophisticated techniques, but in the framework of machine learning. But what's important to say? Important to say that if the machine learning is not well understood, we needed to be able to pay for their mistakes, because sometimes you are doing, for example, galaxy classifications, and we have thousands of elliptical galaxies, thousands of spiral galaxies, and there are few galaxies that are irregular or lenticular, that is inside of the elliptical class, bars in the spiral patterns that are inside the spiral class. And so we can, the AI sometimes can classify in a wrong way a kind of morphology, galaxy morphology. If when it does happen, what's the problem? Someone can take that information and he doesn't care about to see the light curve or to see the morphology. He goes straight forward to the spectra and spend a lot of time working on the spectra, think that object was an elliptical one, for example. Then you see that it was not elliptical, it was a mistake from the AI. So that's why we need to have the explainable AI. It goes to not only for to be explainable, but to be interpretable when we are trying to open the black box for machine learning applications, but also auditability and sometimes accountability, because if there is a mistake in critical areas, we can go to losing time, working time, and sometimes make a very bad decision for critical areas as health, for example, energy, education, and so on.
All right. Thank you, sir.
Thank you very much. Okay, if there is no more comments or questions.
Good day, sir.
Yeah, please, Dinka.
Yes, sir. Thank you very much for the good presentation. So
Thank you.
please, I have a question concerning the representation of data. I heard you quite mention of DFT, density functional theory. I wanted to know the limitation of representing data with it, and on your own opinion, which method you advise us to represent our data or to work with, since there are diverse fields and working with all may be cumbersome sometimes. Thank you.
Okay, that's a very good point. Because we are here talking about statistical analysis. When you say statistical analysis, it depends on very good samples. Okay, and to know if it's a very good sample, we need to have a previous analysis on very good quality data for even application. If I'm working on a supernova, for example, a light curve, and of course I know the results of such a tool that has been applied to this very well-known object. So if I take it a new one, I know what I'm expecting to get from that. So from a statistical analysis, we need, first of all, we need to know exactly what we need to be sure about the statistical quality of the data, okay? Not only on the size of the data, amount of measurements, but also about the availability of those data for a search technique. And this we can be sure only if you have canonical data that we applied before to go forward for new data. That's a very important point. For spectral analysis, spectral also here is a kind of statistics. The right term should be statistical spectral analysis, actually, because we have many statistical metrics implicit in the spectral analysis. Even the autocorrelation function, for example, is based on the mean, right? Everybody knows here that when you apply fast Fourier transform to get the power spectrum density, we are doing the integration of the the fast Fourier of the autocorrelation function using the kernel of a Fourier transform. So Fourier transform inside of an integral function that works on the comparing all the values with the mean. So it's also statistics. So the same criticism that I saw concerning the statistical analysis, it also is valid to spectral one. I'm not sure if I answer your question.
Yes, sir, you did answer my question.
Okay.
Hello, good evening, sir. Can I ask one question?
Good evening. SKS. S means?
Yeah.
What's your name?
Sukhvinder. Sukhvinder.
Sophina. Okay.
So, yeah. Sir, when we are telling that the profile is Gaussian or non-Gaussian for suppose any time series. So, what is what it interpret about the series or the system? If it is Gaussian or if it is non-Gaussian?
Yeah. From the physical point of view, if we have a Gaussian, there are at least three very strong interpretations. Gaussian means the autocorrelation in the signal is very low. You know what happens, let's say, about the memory in the signal. If some thing happens fluctuating 10 days ago or 10 minutes ago or 10 seconds ago, and we compare if it happens now, there is no physical connection. Okay, it's a very stochastic one and with a very low memory in the signal. So Gaussian means like that. So that's the first strong interpretation. The second interpretation is when we have non-Gaussian, the cause of those non-Gaussianity is the extremes fluctuations that appears in the time series. Of course, you need to be sure that such extreme fluctuation is not artificial one. That's the first point. If it's artificial one, so it's a very big problem in the analysis of a non-Gaussianity. But once you are sure that such kind of extremes, positive or negatives, doesn't matter, are real ones in the source, coming from the source, it's showing us that it's a very non-Gaussian, so could be a kind of a memory in the signal. Okay, autocorrelation function can tell us maybe there is a kind of a determinism in the signal. It's not a pure random. There is some determinism in the system that sometimes could be model. But there is a very important point on this kind of non-Gaussianity. That is, if the extreme comes from an endogenous process or exogenous process. When the time series is fluctuating and the extreme comes after a very low frequency fluctuation, it means there is an autocorrelation function that can tell us that there is a memory in the signal. And when it happens, it means endogeny. It means that all the process, nonlinear processes, are very strong in the source, in the underlying process. But when the extreme happens suddenly, there is no autocorrelation function before that. The correlation function is like a white noise. It means that that stream, if it's a real one, the main cause is an external one concerning to the system, the source of the time series or the underlying process. Okay, for example, if you have a kind of interaction among two black holes, okay, and there is some nonlinearity on that, and you are measuring only one of the stars, of the objects, you don't know there is another one there, that's an exogenous one. So we can see suddenly a peak on the second one that is a result from the interaction with one body that it's not in our measurement. So it's a kind of exogeny. So it's a non-Gaussian one, but there is no endogeny. It's exogenous one. Okay, so that's the one very expertise point in this kind of analysis that depends on not only the on the analyzer expertise, but the astronomer or astrophysicist expertise, you know, on that process. And so that's the second strong interpretation. The third one, concerning non-Gaussianity, is trying to find out the best models for non-Gaussianity. So the best PDF in order to validate, as I told you in the 5 minutes ago to the second question, to validate computational models, for example. So it's non-Gaussian, okay. So I go to my simulator and try to get the same non-Gaussian process from simulations. And then with the basics techniques that I showed here, we can do this kind of modeling validation, okay, based on Cullen-Frey graph, based on the spectral index and so on.
Thank you, sir.
Thank you. I appreciate it. So if there is no more questions or comments, I'll move it to the last transparency here, my last slide to close. Okay. So for hands-on, we didn't talk about synthetic time series generation. We can generate different time series, okay, trying to understand the underlying process. If it's what kind of noise is in our data, we need to know the fluctuation patterns coming from different models for noise data. Sometimes you call noise, but noise is also signal. For example, a red noise is a Brownian motion, is very close to diffusion in many different kinds of systems. So we call colored noises, and we know that for each one we have a different spectral index. Okay, so it will be very interesting if you do the hands-on to create colored noises using Python libraries. Okay, I recommend you do that as a hands-on before we go to the second module. I will write that on the booklet, so you find this hands-on, extra hands-on there. But try to generate colored noise. That will be very important in order to test also explainable AI from machine learning applications. Another one is the chaotic signals. Chaotic signals are, in thesis, a deterministic one, but they are unpredictable. Okay, so if you have a pendulum with it, instead to have only one mass, you have two masses, or maybe more than two. you get chaotic, unpredictable, even it's deterministic, you get unpredictable time series for example, variation of the velocity, variation of the position. So we have many chaotic synthetic time series generators. Logistic map is one. I'm going to ask you to perform this model in the booklet, extra hands-on. We have also Raynaud map. We have a Lorentz map. And if we plot the time series against itself, just taking into account a small lag, you take the attractor, okay, in the phase space configuration. From the time series, you just plot itself against, we plot the same time series against itself by a lag, a small lag, you take the attractor. When you have more than one variable in the model, like Lorentz one, we plotted one, and each variable is for one differential equation in the Lorentz system, you get this attractor. So we can play a lot, generate very interesting and complex time series from chaotic signals. So you are going to ask me, but there is a real chaotic behavior in nature? I would say 100% not, but we can have near, close to chaotic mathematical behaviors in nature in many cases. For example, if you take the dynamics between some animals, okay, predators, for example, looking for food, you see that the logistic map can mimic this kind of a behavior for long time series, in long range time series. Also, the same thing for some birds that are flying from long distance. It's a very non-Gaussian one, and the time series is also, sometimes it seems to be modeled by chaotic behavior. Also, earthquakes, dynamics, many nature systems. And also we can have hybrid models. We can mix the, for example, chaotic signals and colored noises and have something more complex. We can have also multifractal time series from the P-model approach. Okay, P-model is based on multiplicative cascades. It means some kind of energy or information comes from one big source and goes to second level sources. And they go 50% of energy, 50 for one side, 50% for the other side. And then starts a multiplicative cascade of information. In multifractal time series, we can deal with no homogeneous cascade. Instead to have 50% of energy for one side and the other side, it goes 30% for one side, 70% for the other side. And so we start no homogeneous cascade. From this kind of models, we can also get very complex fluctuation patterns for time series. Okay, that's what we call multifractal time series modeling. Also, we can have a hybrid, as I told. Sometimes in nature, we don't have for many astronomical processes the real understanding of the underlying process. So we can test a new model based on these synthetic time series generators. Okay, so I recommend you try to do your hands-on in the Colab notebook to generate this kind of time series. Okay, as I said here, there are many behaviors in nature: solar space physics, atmosphere and climate, hydrology, geophysics, river flows, precipitation, earthquake, as I told you, and also astronomy and astrophysics. Okay, there are many pulsar timing residuals, for example, seems to be chaotic. Okay, behavior in the interstellar medium, we know that's weak turbulence, so it's more closer to non-homogeneous cascade than to the Kolmogorov one, Navier-Stokes equation, for example. And so this kind of artificial time series generators can bring us can be useful to bring us to realism in synthetic data, improving actually also those synthetic models, null hypotheses and benchmarks among different tools, understanding mechanisms, underlying mechanism, parameter estimation and inference for modeling validation. It can be applied also to test HISC and extreme pipelines and modeling and simulation of a very, very complex systems as, for example, many radio astronomy in a radio astronomy array, many very complex movements to detect different sources at the same time, or big sources in the sky. So there are many applications, okay? So I recommend you do that. And I say, I promise you, I will provide a course booklet for review and hands-on practice. And thank you very much for your attention. I'll be available those days. If you want, send my mail. I can read and try to answer your questions and improve your comments. And also, we can work together in some astronomical data analysis, even from simulations also. We have high performance simulation in our institute here for plasma physics, solar physics, and also for astrophysics systems, especially for transients, because now we are working hard to face on the LSST data. Okay, so thank you very much. Thank you very much, and see you next week.
Sir, can you hear me? One question.
Yeah, I can. Please.
Sir, this is Kiran from India. First, thank you for delivering an excellent presentation.
Hi, Kiran. Thank you. I appreciate.
So, apart from this course book, can we have access to these slide presentations, slide notes? There's a very good explanation of those things.
Okay. Thank you very much.
These slides.
I'm sorry for the basics. I didn't know the expertise of this kind of class. So I prefer to start from the basics, and for the next one, we go to more complex analysis, and especially using machine learning tools.
Apart from this course book, so we need to have, can we have these slides along with this Colaba notebook?
Yes.
So that will be very good, because we mentioned some reference books also. So it will be healthy to discuss with fellow members or batch members like that.
Fine. Thank you. Okay, Mole, the words is with you. So please.
Yes, no, I'll make the material available on the GitHub repo that we have with that they have access to. But Prof, from our side, thank you so much for such a wonderful presentation. We really appreciate you. This was very detailed as well as elaborate. So I think we'll see you next time with the expandable AI. Thank you so much, Prof.
Thank you very much, all of you, and see you next. Thank you very much.
Bye-bye.
Bye-bye.